All right, hello everybody. Welcome to EEE 135. Today we're going to talk about Chapter 5, Solar Tracking. So, start out with, we need to talk about latitude and longitude. This is a coordinate system on the Earth that we typically use for everything, right? So, Earth is divided into imaginary grid of a sphere. So, kind of think by imaginary line going north to south and then around east to west. Okay. Horizontal circles are called latitude. So these circles like this, these are latitude. You go from 0 degrees, where that's the equator, all the way up north to 90 degrees at the North Pole. And then you could go all from the equator all the way to the South Pole at 90 degrees south. It is to note that the older system used positive 90 degrees and negative 90 degrees, but again, that's confusing. In today's world, we typically just use 90 north, 90 south. Right? That's just there's no way to mistake north and south. Right? So with that being said, we could figure out from the equator how high up we are on the Earth towards the North Pole. Right? Now, we need another coordinate system to lock in our specific location, and that's called longitude. So think about lines drawn from the South Pole all the way to the North, or sorry, from the North Pole all the way down to the South Pole, and we just litter the whole Earth with it in a circular fashion. So these are these lines from north to south. Okay. And what we can do is we could choose a point on the Earth. Greenwich, England, which is an old observatory, they started this system. That's considered 0 degrees. So the longitude line from north to south that goes over Greenwich, England is 0 degrees. When we want to travel east, we can go from 0 degrees to 180 degrees east. So as we travel east, 180 degrees is the exact opposite side of the Earth from Greenwich, England. So think of an imaginary line drawn from north to south on the other side of the Earth, somewhere in the Pacific Ocean. Okay, so that's going to be the 180 degrees. We can also go west instead and say west from 0 to 180 degrees. Okay, so think of traveling around the equator in the Earth. We could go east or west, and we'll go from 0 degrees to 45 to 90, all the way to 180 degrees on the opposite end. And then we could go from 180 degrees back to 0 degrees, except we just have to mark it as an east instead of west, or west instead of east. Okay. Now, the beauty of this, with these two coordinate system, we can pinpoint any location on the Earth with these two. We just need two numbers, 87.3 degrees north and 113.2 degrees east. We have an exact location on our Earth for that. Okay. So latitude and longitude are used in today's world consistently. That's going to have a big play in tracking the sun, because that's where we are on the Earth. We need to know our location on the Earth first before we can start thinking of what path the sun travels over our head. Okay, so we have to imagine we are on the Earth. The Earth is spinning, but we're planted our feet on the Earth. So from our point of view, nothing's changing because we're spinning with the Earth. If you stand still and look absolutely directly up, right, on your flat surface looking up, that is a zenith. So you can think of a line coming out to Earth all the way up. That is a perpendicular line, and that's the zenith. Okay. Now, somebody at the North Pole, if they're looking all the way up, they will notice, for the most part, the sun is going to travel around them at eye level. It might vary a little bit based on the tilt of the Earth, but for the most part, if you look forward, the sun's going to go around you all the way to the back and come back forward to you from your perspective when you're sitting at the North Pole. Okay? Now, the opposite will happen if you're exactly on the equator, in the middle, in the center between North and South Pole, right in the middle, right? This is where, if you look directly up, you're going to see the sun go all the way from the east, go straight above you and behind you to the west. Okay, so it's going to literally go straight over your head, like at the equator for the most part. So which way, these are two extremes. But what it tells you is based on where you are in the Earth, the sun's pattern is going to take a different path. Okay. So when you think about solar tracking, you're going to have to say, well, where in the Earth am I? What's the path of the sun in the sky? You have to calculate that and change your solar panel tilting and where it faces based on this difference. Okay. So different cities have different solar tracking requirements. So it kind of says right here, somewhere in the North Pole will notice that the sun travels at eye level 360 degrees around them during a 24-hour period. Somewhere at the equator will notice that the sun goes from east to west above their head directly in a 12-hour period. Because the other 12 hours, the sun is traveling on the other side of the globe that you don't see. Okay. So the big trick is it's all about perspective from our point of view. Okay? Now, of course, not everyone lives in the equator or the North Pole, so there's a middle ground. And this is where latitude comes in as a helpful number. So the actual degrees of latitude represents how much of an angle the sun's path will take off of its zenith. So for example, if we're living in the northern hemisphere at 40 degrees north latitude, if you stand on the Earth, if you stand on the flat surface on the Earth and you look directly up, that's your zenith. You will observe through the day that the sun is going to go from east to west, but it's going to have a 40-degree tilt towards the south. Right? And that's because you yourself are tilted more north, exactly by 40 degrees. That's what the latitude means. So think of a sphere. You're just, instead of being an equator looking directly at the sun, you're a little bit up north. So when you look up, you're going to miss the sun. The sun is actually kind of traveling a little more south from your point of view. So the arc of the sun is going to be a little bit different. So, and you could go outside and observe that during the day, that the sun will never go up right above your head. It's always going to be kind of tilted to the south. Okay. Sacramento has an added latitude of roughly 38.6 degrees, so it's north, so it's very close to the 4-degree north latitude. Okay. Now, during the fall or summer, if you track the movement of the sun, what path will it take? Okay. So for Sacramento, again, you look straight up. You're going to see that the sun is actually making its arc towards it has a tilt towards the south at exactly by 38.6 degrees. Okay. So that's why latitude is so important, is this number really helps us in determining where the sun travels in the sky. Okay. Now, that's just relative to where we are on the Earth. There's another component of the sun's traveling path, and that's the Earth's tilt. So you remember, somewhere in primary school, you learned that the Earth is tilted on its north-south axis by 23.4 degrees. So it does spin, but it's not spinning completely perpendicular, it's spinning at a tilt. As we rotate around the sun, this tilt, the sun will see different parts of the Earth, right? So think about during the summer, we are tilted more towards the sun. So the sun is right here. We actually tilt closer towards the sun, so the sun is more in our face. That's why it's hotter in the northern hemisphere. Now, while the northern hemisphere has the sun directly at our face, the southern hemisphere, the sun is actually more tilted away. So the southern hemisphere, it's wintertime. Okay. And conversely, in the winter, the sun is tilted further away from us, so it's not going to hit us as hard. And in our winter, it's the southern hemisphere summer. Okay, so if you lived in the northern hemisphere your whole life, it's kind of hard to believe, but Christmas in the southern hemisphere is summertime, where people are running around on the beach. Here, we're freezing our butts off. Okay, the opposite will happen in May. In South America, it's freezing cold while we're here sitting here with 100-degree weather. That's just because we're different parts of the Earth. Okay, so if you live in the northern hemisphere like Sacramento, summer months typically are May, June, July, August, and that's where the Earth is tilted, where we're more directly towards the sun. If you live in the southern hemisphere, the southern months are November, December, January to February, where for the southern hemisphere like South America, they're tilted closer towards the sun. Okay. It's very strange, but if you think about celestial bodies, right, think about the Earth, it is tilted. as it rotates around the sun, the tilt doesn't change, right? It's not like some people think the tilt will kind of move back and forth as we go around the sun. It actually stays the same and just goes around the sun. Okay. And that's why, from our perspective, we see the sun go from the fall to the summer season to winter and spring. Okay. If we didn't have this tilt, it would be the same. It would be the same weather all throughout the year at the specific point where you're at. But obviously, we can't help that, right? So this is kind of a good graph to show you the angle of which the sun tilts on the sky from its normal path. So for example, if we're at 40 degrees north or 38.6 degrees north of Sacramento, right? If we're at this spring or fall equinox, there was no additional degree change from 38.6 degrees. That's just based on where we are in the north. Okay. But in the summertime, we're tilted more towards the sun. So if we look at the sky, the arc the sun takes is not 38.6 degrees. It's actually 38.6 degrees minus 23.6. So in the summer, the sun is actually almost over our head. It's not quite, it's like a little bit off, but not by that much. The peak where we have the most extreme tilt that the sun's in our face is a summer solstice. Okay, so for the northern hemisphere, the summer solstice is approximately June the 20th. It does vary based on 1 or 2 days every year. Okay, and once we're at our extreme, we will then back away and eventually we'll get to the equalization point where the sun is aimed directly at the equator. So we have no additional angle change to our latitude. Okay, this 0 degree where the Earth's tilt will make the sun directly hit the equator, that's called fall and spring equinox. It happens twice a year. Okay. These spring and fall equinoxes are typically March the 20th and September the 22nd, and it varies 1 or 2 days. Okay. The other extreme is where the tilt is so great that we're further away from the sun, or in our perspective, the sun is more tilted to the horizon when it arcs over. So in this winter solstice, the most extreme, normally we have a 40-degree tilt based on the sun path going over our head. We're going to add another 23 degrees. So instead of being 60 degrees going up, instead of going, let's say this is 0 degrees, 40 degrees going this way, we're going to add another 20 degrees and it'll do this, right? So in a very deep winter, you'll never see the sun above you. It's always going to kind of just arc over you like this. Okay, and there's a big difference in how the sun travels across the sky during the summer versus winter months, right? Unless you look up and check every single day, you might not notice, but throughout the year, it does change drastically. Okay. Now, again, why do we care about this? Remember, we need to make sure that the solar panels track these movements to get the optimal output at the end of the day. Okay. This is a good image to show you how much the sun moves across the sky based on the year. So what somebody did is they literally waited till dusk, so like 6 p.m., and they took a picture every 2 weeks or every week, other 2 weeks or every week for the entire year at the exact same time during that week. And you can see that the sun changes its position throughout the year, right? And that's a pretty drastic change, right? That shows you the different arcs that happens between the winter and summer months and other things as well. So if you take a picture at the same time, the same location each week, notice that there's a change to the where the sun's location is at that exact point due to 2 things. One is a tilt of the Earth, and the other one is the Earth's elliptical orbit around the sun. Okay, so first off, the north to south variations. So if you notice, some of these spots where the sun is, some's more north than south, or higher up in the sky versus lower in the sky. That's a tilt of the Earth. It cycles yearly. That's the seasons. Okay, we have east to west variations as well. Why do we have east to west variations? That's because the Earth's orbit is elliptical. So sometimes during the year, we're actually traveling faster around the sun, and other times we're running slower. So remember, it takes a whole year for the Earth to orbit the sun. Some months, because we're physically closer to the sun, because it's like the long edge of the ellipse, we're actually physically traveling faster as we fly past the sun, right? That will give us a east to west movement, right? So like right here, right here, these, you see how they're really far apart? This area is probably these faster areas. That's why it's really, there's a far gap, because each of a week we're traveling faster, so the sun is moving away from us faster. Okay. And then the other edge is where we have our really sharp elliptical bend. We're not changing that much from the sun's distance, so we're not going to get that big of a variation. It's kind of these edges right here. Okay. So even not only the daily movement of the sun, but we have to calculate the yearly movement of the sun, right? And this is a much more complex pattern than just east to west every day. Okay. So there's a whole industry of astronomy tracking the exact movements of celestial bodies, and this is one of their jobs, is to track the sun's movement in the sky. Okay. So it could get very, very complicated. Now we do a really good job. We probably track the Earth's movement for the next like a couple hundred years exactly, right? Because this is all based on gravitational principles and physics. So, and that stuff doesn't change unless there's a drastic, like a star collides or an asteroid knocks us out of orbit. We're going to keep doing the same thing over and over again. It's a very predictable pattern. Okay. So we ask ourselves, why do we even need sun tracking? Well, at the end of the day, remember, it's all about making sure solar panels are correctly aligned to the sun. Okay, so is it necessary to track sun when using renewable solar generation such as this heliostat? For this particular one, absolutely. Because this is a mirror, it'll bounce off the sunlight to this tower. This tower is a very relatively small target. So if you're even off by 1 or 2 degrees, you're going to completely miss the tower and you're going to lose everything. So in this particular case, you need exact locations every minute. And then this heliostat probably changes its position every 15 minutes to make sure we're always accurate, right? And it has to change every 15 minutes as to readjust 365 days out the year. It's a lot of work, okay? But it has to be very precise, so we need the exact coordinates of the sun's movement, okay? What would happen if we're not accurate with our sun tracking? In this particular case, we totally miss a tower and get 0% output. So this is a all or nothing scenario, okay? So absolutely critical for this one. So another one is PV panels. So the ones you put in your house, they can benefit from tracking. It's not absolutely necessary, right? So is it 100% necessary to track the sun for rooftop PV panels and move them? No, not necessarily, because even if the sunlight is not directly facing the solar panel, you still get some amount of sunlight going in and you get some amount of energy, but you're going to get less energy. Okay. A perfect sunlight will shine literally 90 degrees into the panel. So the sunlight literally hits it perpendicular perfectly into the panel. You're going to get the most amount of energy. As your sunlight changes and you're hitting it at an angle, you're going to get less energy, right? And you could find that difference. So, well, I guess let's answer this. So yes, perfect sunlight shines directly into the solar panel, but will we still benefit from sun tracking? Yes, the more direct the sunlight, the more the power output. What's the difference? The more off your sunlight angle is from the perfect angle, you're going to get an efficiency of cosine of theta. So basically, if you're directly on it, where 0 degree difference, you get a cosine of 0 degrees is 1. So you can get 100% efficiency. As you veer off more and more, you're going to get away from 1, you can go towards 0. So if you're at 90 degrees, meaning the sunlight, so this is your perfect angle for the sunlight, and you're 9 degrees off, you're completely missing the solar panel. Cosine 9 degrees is 0. You're going to get nothing, right? If you're 45 degrees off, you're going to get about 70% efficiency. Cosine for 1/2 is cosine inverse 1/2 is 70. Sorry, the cosine of 45 degrees is about 70%, right? So There is some benefits in making sure that the solar panel is directly facing the sun at all times. Okay, and that's how you calculate is the cosine of the angle, right? Other things is for sun tracking is as you move the panels, you have to make sure that you're not blocking other panels. Okay, if we want to add sun tracking, what do we need to add to design the PV system? Well, obviously it needs to move, right? We need to make sure there's some pivoting action or turning action that the panel will literally move as the sun travels throughout the day. Okay. In the morning and nights, we need to make sure we want the sun during the morning and nights, the sun is typically on the horizon, not up above us. So we need to make sure the solar panel tilts more towards the horizon, right? In the morning, we want to make sure it faces to the east. At night, we want to make sure it faces towards the west. Now, there is one thing you gotta watch out for. If you have all your solar panels equal level and you bend them all towards the morning sun, they're all facing east, you might actually block your second solar panel. You see how we're such an extreme angle. The first solar panel is actually blocking some of the area of the second panel. And you're going to lose a lot of power here. It's not proportional to the amount of area you blocked, right? Even blocking a small portion of the solar panel can drastically reduce your output to 80% power loss, right? So this is one thing you definitely want to avoid. You see a bunch of Reddit posts of people in DIY solar. They're like, why isn't my solar panel working? And we're like, dude, because a quarter of your panel is being blocked by the roof's edge or a tree. And you're like, well, I thought I could still get a lot of power even though a little bit of my panel got shaded. And I'm like, nope, doesn't work like that. Don't do that. Okay. So what's the benefits of sun tracking on a daily basis for PV panels is the extra energy you get in the morning and nights. Okay. On average, the sun rises from 6 a.m. to 6 and sets at 6 p.m. So you'll get roughly 12 hours of sunlight to harness. Okay. In the very early morning, there's nothing. In the very late at night, there's nothing. Right. But as the sun comes up in the sky, if you have a fixed PV module where nothing's moving, your incident angle is pretty bad. You can get pretty low power, 50, 60%. About noon during the day, this is when the sun is directly overhead your solar panel. You should get maximum power no matter what. Otherwise, you installed your panel wrong. So around 10 to 11, 12, 1 or 2, this is when you're going to get your maximum amount of power regardless of what you're doing. And then after 2, 3, 4, 5, you're going to start losing. Okay. But if you can do the daily solar tracking, meaning you're turning your panel from east to west on a daily basis, you could get a lot of extra power in that extra morning, right? So when's the best time for solar generation? It's going to be between 9 a.m. and 3 p.m. That's when the sun is clearest. We're going to really start doing some power generation, okay? Now, the red line is how much power you can make with your sun tracking. Notice the big difference between the blue line, which is your fixed no tracking. The greatest points are typically between 8 to 10 because the sun is starting to shine brightly and you are aimed towards the sun. So you see right here above 70%, this flat line, this is where you're directly pointing to the sun from about 9 p.m. to 3 p.m. Okay, this is the best point to get power, to get your energy, and you're tracking your sun, you're pointing your solar panel, you can get the most. Right. So what times of day will you benefit most from added sun tracking to PV's panel design? From 7 a.m. to 10 p.m. and from 3 p.m. to 5 p.m. So think about right here to about right here. This is where we get the biggest differential between the two lines. All this area right here, this is extra energy we're benefiting with solar tracking. Same thing over here, about 3 to 5 p.m. This is where we need the biggest benefit. Okay, this is when the sun rays shine the strongest, but it's not shining directly into the panel. So we're turning the panel to make sure it does shine directly into the panel. Okay, so there's absolutely some benefit for some solar tracking even with standard PV panels that don't need it. Okay. Now, this is where I want to have an example of how do we use all this information to install a solar panel on our house. So remember, what does latitude tell us? Latitude tells us how much the sun is, the sun's path, how much is it off-centered from our zenith looking straight up. Okay. So let's say we need to install a PV panel at our solar site. We need to figure out the correct facing and tilt angle. We are installing this panel in Folsom, California house. Okay. So a tilt angle is the angle between the earth and the panel itself. So for example, you have a flat earth, you have a flat surface of the earth. The solar panel has a bracket that tilts it 15 degrees. So it's facing a certain direction a little bit. So the incident angle is kind of like this. A 60-degree tilt means you're aiming the solar panel pretty far in one direction, right? But the idea is you're supposed to get the sun's path will be perpendicular to this tilt angle. That's the idea. So I could draw real quick. For example, for his 15 degrees path, right? It's gonna let me draw. No, it's not. Oh well. Yeah, there we go. So here for his 15-degree tilt, the sun should shine in this direction, 90 degrees, if we designed it right. Okay. For this tilt at 60 degrees, we want to make sure the sun is shining directly towards us, like so. Right, and that's 90-degree angle. So from an outside point of view, the sun should kind of arc. It's kind of hard to draw like this, where we will get a 90-degree angle from the sun being right here. Okay. Same thing here with the arc. The sun should be right here, shine directly at us. Okay, that's the idea. So how do we do this? What's our criteria? Well, number one, where's Folsom, California? Is it in the northern or southern hemisphere? Okay, and what's the latitude? So we can look that up on Google. Latitude is 38.7 degrees north. So the north latitude means we're in the northern hemisphere. So when we're going to install our solar panel, we need to make sure our solar panel is facing south. Don't face the north because then it's even worse. So make sure the solar panel first is facing towards the south. And then we need to make sure the tilt angle, right, how much tilt we're putting in, is 38.7 degrees because that's our latitude. Okay. That way, remember the Earth is curved. We're kind of on the higher end of the curve where the sun is rotating here. So we need to make sure we bend our panel to where it's perpendicular to the sun as it moves around the Earth. Okay, from our perspective. Okay. So basically, this answer, face south, 38.7 degrees tilt. Okay, that alone is going to be your biggest improvement for solar generation. This is why when people put solar panels on like their car and they drive around the car, they're like, why aren't I getting a lot of energy? I'm like, did you face the solar panel south? They're like, why do I have to do that? I'm like, well, there you go. You just killed probably 70% of all your energy efficiency because you don't know how the sun works, right? You really should go to DIY solar. It's the funniest thing ever, seeing people try to do stuff. Okay, so this is the time where we take our 15-minute break. There's an exercise I want you guys to do in the meantime. It's installing rooftop PV panels. So we're at Redding, California, so a little more north than us. Right? We want to install a rooftop system, a rooftop PV system, but we know this house already has a 35-degree tilt for the roof. So think of the house as on level ground. The roof already is tilted 35 degrees, aiming south and north. Okay. So how much additional tilt do you have to install into the solar panel on the rooftop to make sure we get the ideal, best solar energy out? So I want you to find, you guys can't see that. Will this one work? I want you guys, that's even worse. All right, not as good. I want you guys to find this angle right here. You already have the angle of the house. What's this extra angle bracket we need? That's what I want you to find. Okay. So Go ahead and figure it out. A little algebra. It's a little more involved than what we just did. Just take into account just 35 degrees. Tell me what direction we face it at, and how much of this angle bracket do we need. Okay. So good luck. We'll come back a little bit and check your work and keep on going. So see you in a little bit. All right, hello everybody. Welcome back to EEE 135, Chapter 5, Solar Tracking. Coming back for a 50-minute break, and let's check out this exercise. So remember, we want to install rooftop PV panels. We're going in Redding, California, so we got to look. Redding's latitude is 40.6 degrees north. So for sure, northern hemisphere, we got to make sure solar panels are installed southward facing. Yeah, step number one. Step number two, the total tilt from ground level needs to be 40.6 degrees based on our latitude. We already have a 35 degrees rooftop slant pointing south. So all we have to do is put an additional, well, 40.6 minus 35. We just got to put additional 5.6 degree spacer right here, or bracket right here, to create a little more additional tilt facing south. So here's the rooftop, and notice that we just put a little bracket over here, maybe exaggerate a little bit from drawing, and a panel should be facing south, and that's it. Right? So it's just basic rule of thumb. Anytime you're going to install solar panels, follow this rule. All right. All right. So let's start talking about tracking with the variations of the sun from day to day and other things. So single axis tracking means we only track one axis of movement. The most important movement is the east to west movement. It happens daily, and if you track east to west, you're going to get the most benefit out of anything else. Okay. In the morning, the solar panels need to face east towards the sun. During the day, it should travel from east to west and end facing west at sunset. Okay, so notice east, the sun will track across the day. Our panel needs to move in synchronism with the sun until nighttime. Okay. Now, this is another very important part. When it's nighttime, the panel is facing west. We need to have a mechanism that will realign it and change it back to east for the next day. So during the nighttime, your solar panel system must be smart enough to reset its position from west back to east. Okay. You could do this with a microcontroller. You could do it with passive mechanical systems, but whatever happens at night, you need to reset your position. And this needs to happen every 24 hours. It's a daily thing, and this should happen pretty much in all perpetuity while you have your tracker active. Okay. So most important, east to west movement. We also have a little bit of north to south movement. Excuse me. Now, the north to south movement is not daily, it's seasonally. Remember, the Earth has a tilt of 23.6 degrees. So the sun's path, the arc across the daily arc of the sun will change from north, will move north and south. Kind of like, think of drawing the arc. The arc will bend north to south seasonally. Okay. So in the summer, we're going to have our 38.6 degrees, subtract this difference, and we're going to need the tilt on our solar panel needs to be less because the summer we're more direct. Okay. And at the winter time, we need to add some level of degrees because the sun will be facing more, it'll be more angled towards the horizon because we're further away from the sun. Okay. So this panel tilt needs to happen ideally seasonally. Okay. It's a kind of good image to show. In the summer, the sun is more directly overhead, the arc, and our panel should be tilted flatter towards the earth. In the spring and fall equinox, this is where it's the sun, the angle between the sun and the perpendicular zenith is what the latitude is. So this is our original design tilt angle. Okay. And in the summer, we should add a little bit more because the sun is, the winter, we should add a little bit more because the sun's going to be closer to the horizon. The arc will be more, the arc will travel the horizon back more than it would in the middle of the sky. Okay. So we have seasonal changes in the northern hemisphere. You can climb up on your roof, and every season, aka every 3 months, you could change the bracket, or it's probably adjustable. You can unbolt it and change the angle if you want to get a little bit extra efficiency out of your system. During the summer, right here, take your latitude and in general subtract 15 degrees. You don't want to subtract 23.6 because 23.6 only happens once a day, one day after summer. You want to kind of get a good middle ground, and 15-degree off is a good middle ground. Take your latitude, subtract 15 degrees, bend it back a little bit. That's your summer setting. Okay. After summer comes fall, where you should go back on your roof and add that 15 degrees back in, and this is your standard tilt based on your latitude. Okay. And then winter starts, add in an extra 15 degrees. And your tilt will be more aggressive. And then come back to spring, go back to the original latitude, and then we're back to summer where you're going to go back to negative 15 degrees. So you're just going to tilt it up and down plus or minus 15 degrees based on the seasonal changes. Okay. Now, obviously, most people are lazy. They're not going to do this. They're just going to keep it at the spring and fall setting. But if you want to eke out a little bit more power, you don't mind climbing on the roof and changing this, or maybe it's on your backyard and the ground, then yeah, go ahead and change it. Okay. So those are our two types of tracking. We have east to west and north to south. Okay. Now, let's talk about how the mechanism to do the sun tracking. Let's concentrate on east to west movement because that's the most benefit. So a passive sun tracker means that there is a mechanical system that does not require external power source. That's what passive means. That will automatically do the sun tracking for us. So what you can do is, it's a pretty complicated system, but it does work, where you have two boxes, clear boxes with liquid inside it, and you have like these little shaders. So so in the morning, you have the panel, and it's probably it's probably flat with the earth. The sunlight's going to hit it. Now, these black shaders will shade off one part of this canister, so nothing's going to happen. But the sunlight will hit the other canister because there's no shading for it, and it'll actually boil the water. Okay, and as the unshaded liquid will start boiling, it'll increase volume, and then it's going to push the liquid to the other canister, and then there'll be more weight on the other side because you're pushing the liquid. So by boiling water in one canister and forcing the rest of the liquid in the other, you're creating an undistributed amount of weight, and it'll tilt. And it's going to keep tilting until the sunlight is equal on both sides of the canisters, and that's the equilibrium you get. Okay? So it's kind of a passive system that uses gravity and volume and liquid to redistribute weight, and it'll slowly move with the sun. Okay? Now, what happens at night? At night, there's no more sun. The liquid will stabilize to where you'll have a 50-50 distribution for liquid, and then it'll kind of be flat in the middle at the sunlight. So, sorry, at night, it will turn flat. So in the morning, the sun will hit from the one side, it'll start tilting towards it, and then as the day moves, it'll naturally follow it because it's trying to equalize the weight between the two canisters. Okay? It is a very slow system. It's always going to lag behind the sun a little bit because it's a purely reactive system, but it's free in the sense that we don't have external power, right? So, I mean, it's a system that works. Okay, so that's a passive system. You can have active sun trackings where we have external power, which is a motor, most likely a DC motor, to turn the panel for us. Okay, so for example, there's two types. One is you have a pivot right here, a joint, and the panel will literally move, and it'll pivot like this. Okay, and it'll start from the east, and the panel will pivot across to the west, and then at night it's smart. There's a microcontroller here. It'll reset again. So you could literally have a DC motor and a microcontroller, and program will change maybe 1 degree every 5 minutes. Okay. And then it will just move with predetermined steps that you program. And at night, maybe at 2 in the morning, it will just reverse immediately for the next day. So you can you can literally program with an Arduino board, whatever you want for a microcontroller. The other option is to have the whole base of the panel swivel. So think of like a disc on the ground, you're just turning. So then this panel will turn circular and aim, it'll kind of aim towards the sun here, and it'll just start aiming and changing directions as it moves across the sky. So think of like you have a panel, and then instead of doing this, it just rotates like this, right? And as long as you're aiming up and just rotate it around, you'll catch the majority of the sun. Okay. So, yep. What are the two types of single axis tracking? Horizontal axis, where the panel literally just tilts 180 degrees from east to west, or vertical axis, where the panel swivels 180 degrees on the pedestal. Okay. How do we actually move the DC panels? You have to use DC motors, right? It's kind of convenient because you use DC motors to have high starting torque, right? You don't need a lot of speed for this, but you need a lot of power because solar panels are heavy. And the power supply is already there because the solar panels output DC power to begin with. So it's kind of both the best worlds. You naturally will use a DC motor for this application. Okay. Here we could talk about horizontal axis tracking, that east to west movement, right? So for daily solar tracking, remember we have to use east to west movement. Assuming we use a horizontal axis movement, which way do we orient the axis of movement? You can orient it north to south. So remember, we need to make sure we pivot east to west. So the axis of pivot needs to be from north to south. So for example, look at this trough right here. If we draw an imaginary line through the trough, at the end of the trough, it will be pointing north. Where we're at now, we look behind us, it will be pointing south. So the trough is going to pivot across the north to south axis. Okay. Same thing with this panel to the left. You can see how it's going to pivot kind of like this, right? And the axis of movement is like this, and that's going to be north to south. Okay, so that's the movement we're talking about. What is a typical rate we have to move? Well, remember there's 12 hours, right? 12 hours of sunlight from east to west. We have 180 degrees of movement. So it's very easy. You take 180 degrees divided by 12 hours, you get 15 degrees per hour. And you can split that up even more, right? So you could say, what is it? 15 degrees in 60 minutes. Every 4 minutes, you have to move 1 degree, right? And again, you could program that in a microcontroller for a DC motor pretty easily. Okay, so that's your horizontal axis tracking. East to west is always the most important. Now, we could go even more detailed, and we could do dual axis tracking. So not only are we tracking the east to west movement, we will also track the north to south movement. So you see right here, we have our daily east to west movement, but notice during the December to 21st to June to 21st, the path changed in the sky. We have a pretty large angle difference. And this is about 45 degrees, right? It's 23.6 degrees times 2. Okay, so that needs to be tracked as well if we're using those concentrated solar panels. We're using any type of mirrors or lenses. They need to have exact tracking, so you have to use dual axis tracking for some of our solar applications. Okay, so why is north to south axis and east to west axis not so? Question is, how do we actually track this legitimately? Well, north to south axis and east to west tracking isn't exactly enough, because that's only going to give us a bird. If you look from the bird's eye view looking into the earth, it's only going to point where the sun is from the sky, right? What it's not going to tell you is what's my tilt angle from the ground looking up, because we're at the ground. Not only do we need to know where the sun is, we need to know how much do we have to take our panel and tilt it up to aim at the actual sun. So we're missing some information here. So a lot of astronomers, the astronomy community, figured that coordinate system, like the longitude, latitude, is not enough. We need something more detailed. And we decided to use a altitude azimuth tracker. This is instead of a 3D system with three variables, because technically we could use X, Y, Z coordinates. That would work. Keeping track of three variables is complicated. So we borrowed from calculus 3 spherical coordinates. If you remember spherical coordinates, is think of a sphere. All we need is the angle from a set point. So think about on the Earth, we say this is north. We could then travel clockwise a certain angle and stop. That's an azimuth angle. Once we have that, from our point of view, we could then tilt our vision up by a certain degree. This is called altitude degree. And once we have those 2 points, we could then look in the sky and see the sun directly. So that's spherical coordinates. It's 2 angles based on a pivot of the azimuth and a pivot at altitude. Now, in raw spherical coordinates, there's a third variable called the magnitude. What's the distance between us and the point? Now, as solar tracking, we don't need the distance. We don't care. It's really far anyway, it's the sun, all right? So we could throw away the magnitude. All we care about is the 2 angles, okay? So the azimuth angle is how much clockwise spin do we need from a north-facing point. North is 0 degrees, and we could go all the way to 360 degrees, okay? Altitude angle is looking at the horizon and then aiming up by a certain degree. So we look at the horizon and we aim up, and we could go from 0 degrees where we're literally facing the horizon all the way to 90 degrees where we're looking straight up. And there's a variation between 0 degrees and 90 degrees, okay? So those are your 2 angles. How do we use that? Well, conveniently, the most efficient way to design a dual axis tracking system is to have a solar panel on a pivot, on a pedestal that pivots, okay? So first off, think of like your computer chair. So I'm sitting in a computer chair. First thing I would do if I have my panel, I would pivot 360 degrees however I want to get to the sun, and that's my azimuth angle, okay? So we have a DC motor to do that. And then once I get the correct angle, the azimuth angle, then I could tilt my chair back like this and then get the altitude angle, right? So that's how these solar panels work. So it's literally like your computer chair where you're swiveling and then tilting back. And then with those 2 coordinates, you could get the exact position of the sun at any point in time, right? So here, look at this panel. We have a DC motor to swivel around 360 degrees on its base. And then we have a really powerful DC motor to tilt from 0 degrees all the way to 90 degrees. And that's enough freedom of movement to get any point in the sky we could directly face, okay? Here's kind of another image of it to where you can see the rotation of the pedestal. That's an azimuth angle. And then the actual panel itself tilting, that's an altitude angle. Okay. Whereas the big advantages of the altitude azimuth mounted solar panels, DC motors can naturally accommodate this angle movement. It's very easy to put a DC motor, put some gearings in it, and get this type of movement, right? And that's literally what we do, okay? So how do we implement this? Kind of a little raw image, but you have a DC motor right here that will pivot 360 degrees, and then you have a base on the disc or the pedestal, and then we have another DC motor that will do the swiveling of the panel itself. And all you got to do is just have these 2 controllers linked together and just literally put in the degrees, and then it'll know which position it's at, and then the motor will run to the new position. Okay. So what kind of equipment do we install to accommodate dual axis tracking? We use DC motors and some gearing systems for higher torque. Hardware typically are rotating based on some hinges and some support structure. Okay. Where do we get the accurate information for sun positions? That's also the big question. We do not do it on our own. It's too complicated. Military and weather services typically have 24/7 apps and API data feed that you can get from the National Weather Service and plug it into a DC motor. So the DC motor is literally just going to get two angles, and it's going to do its own thing and then realign to that angle. It's not smart enough to know, oh, at on February the 15th at 3 p.m. we should do this. Okay, we don't need that anymore. We got the centralized weather services to give us that constant data throughout the year to where our motor controller is just doing what it's told. And all dual axis solar tracking system will typically have this type of setup. Get some information from the weather service and just move according to what they tell us to do. Okay. So in summary, that's solar tracking, right? Number one, remember your position on Earth is represented by two coordinate systems, latitude and longitude. Due to the Earth's tilt, we have several important days due to the summer's position and seasons. We have summer solstice, which is the maximum angle tilt to where we're facing the sun directly in the summer. In the winter is another maximum of the Earth's tilt where we're facing the farthest away from the sun, called the winter solstice. Spring and fall equinoxes is when the sun is directly at the equator, to where we're kind of in the northern hemisphere, we're kind of in the middle. Okay. Solar panels benefit from the single axis tracking of east to west movement first. So if you're going to do any amount of tracking, it's always the daily east to west movement. Okay. Where would you install your solar panel by following the rules for a northern hemisphere house? Install facing south. That's a start. And then tilt south by the latitude degrees. Okay. You might want to change plus or minus 15 degrees for summer and winter seasons if you want to get a little extra efficiency out of your PV systems on your rooftop. For more advanced solar resources like solar towers, concentrated PV cells, the mirrors and lenses and all that Stirling engine stuff, we're going to need dual axis tracking. It's a lot more complicated, where we're going to use an altitude to azimuth algorithm with two angles. We're going to feed that to the motor controller to control the DC motors, and that will ultimately move the solar panels on a probably every 5 minutes or every 15 minutes. It'll do calculation and move the solar panel accordingly. And this will happen throughout the whole year as long as you want to keep that solar resource in service. Okay. So that's all I have for today. Thanks for showing up and learning about solar tracking and listening. We're going to come back next week and we're going to talk about the DC motors that control these and kind of some basic operating principles. That way, if you ever get into sizing DC motors, designing them, you have something to talk about. Okay. So with that being said, hope you guys have a good rest of the day and we'll catch you later on. So see you around.